cycle detection, and topological sorting. And finally, DFS. Thus, an application. So this would be the pipeline of things. So we will start with the idea of what is DFS. Depth first search, or DFS, is a systematic method of visiting the vertices of a graph. Its general step requires that if we are currently visiting vertex U, then we next visit a vertex adjacent to U, which has not been visited so far. Note that there are quite a few keywords. Okay. First, it's a systematic method of visiting vertices of a graph. Okay. The step requires that if we are currently visiting a vertex U, then we next visit a vertex adjacent to U, which has not been visited so far. So I remind you that adjacent means a neighbor of U in the graph. Just to recap. Okay. Now, if no such vertex exists, then we return to the vertex visited just before, and the search is repeated until every vertex in the graph has been visited. Again, note there are a few important things. So if there is no further such vertex which are neighbors of U and has still not been visited, then we go back to the vertex that was visited just before and do a search, okay, until every vertex in the graph has been visited. So this part actually, if you look at it carefully, it tells you that we are doing some sort of a recursive call here. Okay, so basically, if you do not find the neighbors of a particular node that are not already visited, then you go back to the ancestor of that node and you look at the neighbors that have so far not been visited of those ancestors. If all the nodes that are neighbors of the ancestor are also visited, then you go to the ancestor's ancestor and you keep on doing this. So there is a recursion embedded in this strategy. Okay, so we will look at it into more details now. So DFS, why depth first? So DFS actually uses, as we have already seen from the previous slide, that DFS uses a strategy that searches deeper and deeper into the network. Okay, so again, deeper and deeper. So this is where it derives its name from, depth first. Okay, so goes along a depth unless all the vertices along that depth have been visited. Have been already visited. So in the pseudocode that we will write just now, there are certain things that we will use, certain notations that we will use. Okay, so initially all nodes, okay, are initialized to color white. Okay, so this white color node also indicates that the node is undiscovered. The node is undiscovered so far. Okay. And we will also set the parents of each vertex to null. These are the two initialization steps. Okay, so now our procedure will begin. We will begin by selecting a node, say U, from the graph. And set its color to gray. Okay, to indicate that the node has now been discovered or visited. Okay. And we will assign to this node a discovery time zero. Okay. The discovery time associated with this node will be 0. Now, for each v which is a neighbor of u, and is still marked it, we visit it recursively. So this means we go to V, and then from V we mark it gray, and then go to one of the neighbors of V, and we keep on doing it until and unless we have exhausted that path, and then we come back. Okay. So if no white descendant of V exists, then we mark V as black in color. Okay. So at this point, we assign a finishing time to the node V. Okay. So like the discovery time, we also assign a finishing time to the node V. Okay. And from here, we return to the ancestor of V, which we will term as pi of V for further exploration. So again, in a nutshell, you start from a particular node, you color it gray. Initially, all nodes are white. You start from a particular node U, color it gray. Now you look at one of its neighbor V. If it is white, you color it gray, and you keep on doing this recursively. And once a particular vertex has all its descendants marked as gray, that is, they are visited, you mark that particular node as black, that is, all its descendants have been visited. And now you go back to the ancestor of that node, and you keep doing further exploration. So as you understand, there is a recursion involved in the whole process. Okay. And we will see how we implement this. Okay, it's a very simple algorithm. We will see how we implement this using a small pseudocode. algorithm DFS of a graph G. Input graph Now you can feed the input either as an adjacency matrix or an adjacency list. Output the depth first tree or forest, whatever the case may be, of the graph G. DFS G. For each vertex U in V, do color of U is set to white, ancestor of U is set to null, and out of for loop time is set to 0. Now for each vertex U in V, do if color of U is white, then call the function DFS visit U. Okay. Now DFS visit is a recursive function which is written as follows. Color U is set to, as we said, is set to gray. That is, U is discovered. DU is set to time. So DU is the discovery time. D is the discovery time. Time is incremented. Now, for each V, which is a neighbor of U, represented by ADJU, do if color of V is white, then make U the ancestor of V and call DFS visit V recursively. So this is where you are exploring the edge UV. Once this is over, color of U, that is, at this time you are sure that all the neighbors of U have become non-white. Okay, color of U becomes black. So this means exploration of U done. And if U is set to time and time is again incremented. So this FU here is the finish time. So now you see, after the complete exploration of the graph, all nodes will become black in color and will have a discovery time as well as a finish time. Okay, and the DFS traversal will be stored in the IV structure, right? This could be an array, this could be a structure depending on your implementation. Okay. So the complexity is very simple. Okay, this part takes order n, where, so let us say mod V is n and mod E is n. And DFS visit has to explore every edge. Okay, since it has to explore every edge, so therefore this will be order m. Okay, so the initialization is order n. So this is the initialization. This is order n, and the DFS visit, since it has to explore all the edges, okay, through this adjacency list traversal. Okay, so this exploration can take order m time, and therefore the order of the whole algorithm is m plus n. So a DFS algorithm takes order m plus n time. So this is order m, as we said, and the initialization is order n. Okay, so we will trace this using an example so that it becomes clear to you. So after the traversal, actually what we land up to is a depth first tree. Okay, and this maps exactly as the DFS visit calls. Okay. Since your U is equal to pi v if and only if DFS visit was called during a search of U's adjacency list or matrix, whatever representation you are using. Okay, so now we will trace an example to exactly see how the algorithm works. So I will show you some of these steps, and then as a homework you will do the rest of the steps. I'll show you the initial steps and the final result. As a homework you should do the rest of the steps. So let us say we have a graph like this. So let us assume that this is our graph. To start with. So this is a directed graph with directed edges. Okay, and we start, say, our exploration or our traversal from U. So traversal starts from U. Okay, so since I do not have a gray color, I will use a blue color to represent the gray color. So please bear with me. So the blue color will actually represent the gray color. It's all the same. So we, as I said, we start with U, and now inside the edges I will write the start and the finish times. First, let us draw the graph again. So as you start your exploration, U becomes gray in color, okay, and the discovery time is set to 1, and we still don't know, the exploration is on, we still don't know when it will reach the finish time. Okay, in the next step, what we will do, we will take one of the edges. Okay, from u. Let's say we take the edge u to v. So we explore u to v. We could have also explored u to y. So this tells you why the DFS tree that we will get finally might be not necessarily the same. Depending on the path of exploration that we are taking, we might get different variants of the DFS tree. So one of the trees that we will land up to is what we are drawing here. So let's say we take up the edge uv. Then in the next step we have so now the node V has been marked gray. Okay, and its discovery time is set to 2. We don't know the finish time. Okay, now in the next step, let's say from 2 we have only one edge to explore, that is VW. Okay, from V we have only one edge to explore, that is VW. So we will explore that and go to the next state of the graph. Now you see U is explored, V is explored, and also W is explored. And we also have the discovery times for them. Okay. So after this, what should be the next step? From W, there is no edge which can be further explored, right? From W, there is no edge that can be further explored. So now, as per the algorithm, we will come back to its ancestor, which is 2 in this case. Sorry, which is V in this case. So from W, since there is nothing to explore further, we will come back to V. Now you see in this stage, in this particular stage, since there is no further white nodes that can be explored from W, so W becomes black. Okay, and now along with the start time of W, we can also assign the finish time of W. Okay, and we come back to V. Now again, from V, we have no other edges to explore. Okay, when we are at V, we have no further edges to explore. So therefore, in the next step, the state of the graph will be as follows. Now, 2 has also become, sorry, V has also become black. Along with W, P has also become black because there is no other white node left to be explored from V anymore. And we now also have the finish time of V. Okay, so in this way the exploration continues. Now after this, from this step you will go to 1, and from 1 you will have another vertex, another white vertex that is left to be explored. You will explore this. Okay, and from there you could have gone to V, or you could have gone to X. You would take any one of the course. V, since it is explored, you will not take that path. You will take the unexplored path, and then you will finish here. And then after that you will, so since the set of nodes are still not exhausted, you will go to Q, and then from Q we will explore Z, and your exploration will stop there because there is no other node in the whole network which has not been visited. So the final snapshot would look as follows. So at this point, in the final snapshot, everything will be black. So in this way, we will complete the exploration of the whole graph. So your final DFS tree would look like, if you now look at your pie, okay, then you will easily get the final DFS tree. U, V, W, Y, X, Q. This is why we said that you might also land up into a forest. This is an example where we land up into a forest actually. So there are two trees, one here and one here. Okay. So once we have got our hands dirty with the idea of DFS, we can now discuss another important aspect called edge classification. So there are basically four types of edges. The first one is called a tree edge. So this is edge UV is a tree edge if V was first discovered by exploring the edge UV. So remember the word first discovered. Okay. If V was first discovered by exploring edge UV. Okay. So the tree edge therefore establishes a direct relation between a node and its ancestors. Sorry, node and its direct descendants. Okay. In other words, the discovery time of U is strictly less than the discovery time of V. Okay. Sometimes we call this a low to high nodes connection. Okay. Or a low to high node relation. So this is a direct So it's a relation between a node and its direct descendants. Okay. This is what we need to remember. Next comes back edge. Those non-tree edges UV that connect a vertex U to an ancestor of U. So a back edge actually establishes a descendant to an ancestor relationship. Okay. Sometimes this is termed as high to low nodes. The next in line is a forward edge. Non-tree edges connecting a vertex U to a descendant V. Again, they establish an ancestor to descendant relationship. Okay. So these again are low to high nodes. However, these are non-tree, okay, non-tree low to high nodes. So the tree edges are direct descendants. These are non-tree edges. Okay, we will soon see an example and things will be more clear. The last one is a cross edge. All other edges that cannot be classified into any one of the above classes. Okay, so there is no ancestor descendant relationship. They are again high to low nodes. Okay, so let us take an example and understand the different types of edges. Let us say we have a small graph like this. So here, if this is a graph, see, I have intentionally colored it in different way. So some edges are colored green. So these green edges are, you immediately understand, these are tree edges. Okay, so involving direct descendants and first exploration. Okay, now the blue edge is what we call a forward edge. Okay, so you see, this is a non-tree edge, but it is also low to high, and it's a forward edge. The red edge is a back edge. Okay, it's again a non-tree edge, and it has a high to low connection. Okay, and finally, the black colored edge is the cross edge. It has no ancestor descendant relationship. However, note that this is also a high to low, and this is also a high to low. The tree edge and the forward edge distinction is easy because one is a direct descendant, okay, and reached through first exploration, while the other is not. However, the difference between back edge and cross edge is not so apparent. So the question is then how to distinguish between a back edge and a cross edge. Okay, it's not so difficult. We proceed as follows. Okay, so both of them are, as you understand, non-tree edges. Now starting, let us say, consider the non-tree edge UV. Okay. Now starting from U, okay, traverse the depth first tree to visit U's ancestors. If V is found in the ancestry list somewhere, then UV is a back edge. Else, if we reach the root of the tree without finding V as an ancestor, then UV is a cross edge. Okay, so if you have explored the full ancestry list and still you have not found V, then UV is a cross edge. Otherwise, UV is a back edge. So in the next class, we'll stop here. In the next class, we will discuss the different applications of DFS, followed by introduction to BFS and one of its applications. Thank you.
Swayam Prabha, Digital India, Educated India.
Hello and welcome to lecture 44 of the course Computational Complexity. So today in this lecture we will see a connection between randomized algorithms and circuit complexity, right? So we will see this this language which we had briefly seen during when we talked about a randomized algorithm called polynomial identity testing, okay, and short PIT. So what is polynomial identity testing? We'll see that, and then we will see an application to of polynomial identity set testing to a problem of determining whether a given bipartite graph has a perfect matching. And then that would imply that that problem of determining whether a perfect bipartite graph has a perfect matching, this problem is in a class called randomized NC. Okay, right. So polynomial identity testing simply is asking if given two polynomials f and g, it's simply asking whether f and g are the same polynomial. Okay, so one may think, what is the big deal to just compare the two polynomials? The catch is that these two polynomials need not be given in the exact same format, right? If there is a standardized format, such as the leading term has the highest degree, then the second term has the second largest degree, or some standardized format, then it's just a matter of checking between the two. But then even the way the polynomials are specified itself could be in different ways, right? So this may require us to do some computation. So just to give an example, what if the polynomials are f and g are given like this: x minus 1 plus multiplied by x plus 3 multiplied by x minus 6, and like this, x cubed plus 4x squared minus 12x plus 18. This is g. So now how would you do this? So you can try to reduce the polynomials to the standard form. But on the first look, both of these, the leading terms look like x cube, so that seems to be same. The constant term here is plus 18 in the left hand side, and in the right hand side, sorry, in the right hand side it is plus 18, in the left hand side it is minus 6 times plus 3 times minus 1, which is also plus 18. But then when you look at the coefficient of x squared, right, it will be just the sum of this minus 6 plus 3 minus 1, so it will be minus 4, whereas for g it is plus 4. So you see that these are not the same, right? So one approach is to standardize the polynomial and compare, and this can be done for univariate polynomials. So univariate means polynomials of a single variable, such as this. Here the only variable in f and g above is x, but if you have multiple variables, let's say the number of variables is n, then potentially you could have many such factors like x1 plus x2 multiplied by x3 plus x4 multiplied by x1 plus x6 multiplied by x1 plus x7, some lot of terms, and when you try to multiply them all, it could result in an exponentially large polynomial, right? So the given polynomial may be in a very crisp short format, but when you try to expand them, it could result in an exponentially long polynomial, and this will make our algorithm non-polynomial time, right? So this will lead to a not inefficient algorithm. So this is not something we want to do, right? So this problem for multivariate polynomials in particular can be hard, and in fact, as of now, right, as of today, we don't know an efficient algorithm for this problem, polynomial identity testing, when the input polynomials are multivariate. So when the input polynomials are single variable, then it is easy. You could just x minus 1 into x plus 3, you could just multiply them out, and this can be done efficiently, but not so in the case of multivariate polynomials. So let us try a very simple randomized algorithm. I think I touched upon this while discussing randomized algorithms myself, but still I will just quickly go through it. So choose a random number, okay, in place of x. So let us say we choose r from, and instead of saying choose a random number without any without specifying from where, let us say we choose a random number from a fixed set S. Okay, so this could be some, so let's say it is degree 10 polynomial, so S could be some set of size 1000, right? So you could say S is for example, right, for example S could be just the first 1000 natural numbers, right? So S could be anything. Now you and from that S you randomly pick a number R. Now you evaluate the polynomial f, right? So it's one thing to simplify the polynomial, it's another thing to evaluate it. So now suppose R is let's say 10, right? So for G here you have 10 cubed plus 4 into 10 square minus 12 into 10 plus 18, right? So 1000 plus 400 minus 120 plus 18, you can compute that. For F it is just 10 minus 1 9, 10 plus 3 13, 10 minus 6 4. So 9 times 13 times 4, it's a product, right? So it's one thing to evaluate and one thing to expand without evaluating, right? So just evaluate the polynomials at R, both the polynomials, and then check whether they are the same. And if the evaluations happen to be the same, you say the polynomials are equal, right? And if the polynomials are identical, if the evaluations are different, then you say the polynomials are not identical, right? So this is the polynomial. This is a very simple, right, randomized algorithm. In fact, there is one thing that you will keep seeing whenever you encounter randomized algorithms. The algorithm that you see usually will be extremely simple to describe and program. But the proofs may be long. The proof of correctness or proof of running time, this could be long. But the algorithm itself is usually very simple. So how simpler could it have been, right? You have two polynomials that you want to determine whether they are identical. You just substitute random values and check whether they are the same. They evaluate to the same value. So now the correctness. Let's see the correctness. Suppose let's say when you evaluate the polynomial at 10, let's say, now f of 10 is different from g of 10. This necessarily means that the polynomials are different, because if the polynomial were the same, then you evaluate it at any x, they should give the same evaluation, right? So if f and g are the same, then at any point r, they will always give the correct same evaluation, and therefore if f and g are the same, you will always output the correct answer. We will always say it is identical. However, if f and g are not the same, right, in that case, there is a small possibility that you may end up getting an r for which the polynomials could be different, but the r led you to saying that the r forced you to say that f and g are the same, even though they are different, right? So just as a simple example, maybe let's say if you have x squared and let's say x squared plus 10x, let's say x squared plus 2 and x squared plus 10x plus 2. Right? At x is equal to 0, these two polynomials are different, x squared plus 2 and x squared plus 10x plus 2. But at x is equal to 0, you see that they both evaluated 2. Right? So this is an example of a case. So which are the r for which f and so the point is that there may be r for which f and g get evaluated to the same value, and this is the only possibility of error. So even though the polynomials are the same, it could so happen that you pick an r for which they evaluate to the same value. So what is the probability of error? The probability of error happens only when f is not equal to g, or f and g are different polynomials. Right? When f and g are the same polynomial, there is no error. Right? But the error happens when f and g are not equal, but fr and gr are the same. And this happens when r is a root of the difference polynomial. Right? The difference is f minus g. So here what happened here? X squared plus 2 and x squared plus 10x plus 2, the difference is, so the difference is simply x squared cancels, 2 cancels, it's just simply the polynomial 10x. So here the choice x is equal to 0 happens to be a root of 10x, right? That's what happened here. And it could happen in different ways. So r is a root of f minus g. But we have what is called the fundamental theorem of algebra, which says that if a polynomial is of a certain degree, then let's say degree d, then it has at most d roots. Okay, so if f and g are of degree d, then the difference is also degree d, right? At most d, maybe even smaller, and in that case the difference has at most d roots. And you picked r from a big enough set, right? So if you recall, we picked r from a set of size 100d, right?